In our notes, I'm going to add on to the notes that we did from our last class, which were these trig equations. I'm going to actually rename this, and I'm going to rename it to solving equations. And you probably should do the same thing because eventually we will take a quiz over this specific document. Okay, so we're going to solve like all kinds of equations. And we were just doing that in our last class. We were solving trig equations. And that's what your Delta Math homework was. All right, so before we go on though to solving some other types of equations, we're going to kind of take an in-between step and talk today a little bit about complex numbers. And then because we'll need this skill to be able to do our next lesson, okay? And I'll first do a little review refresher. I know back in your glory days of algebra, you guys simplified radicals. Like if we had the square root of 12. Remember we had those factor tree things? So we could split 12 into like root 2 times root 6, and then split 6 into root 2 times root 3. And then you tried to find pairs. So like we have a pair here, and if the pair are the same number, that number goes on the outside and the other one stays underneath. And so that simplifies into 2 root 3. Okay. Now, some of you may have been taught that another way also, and this either way is perfectly fine. Another way to figure out the square root of 12 is to look for perfect squares that go into that. Just kind of like, which is kind of why we just did that Kahoots, because it can save you some time. Like maybe you realize that 4 is a perfect square, and you say, all right, well, I know that that's root 4 times root 3, and then root 4 is 2. So that becomes 2 root 3. So it's, a little bit of a shortcut. Little less work here than over here is kind of the idea if you find perfect squares. But we get the same answer regardless. So if we wanted to find the square root of 200, we could do a factor tree. So let's see, we could break that into 2. I know it's even, so 2 times 100. And I know 100 is 2 times 50. And I know 50 is 2 times 25. And I know 25 is 5 times 5. And so we're doing that factor tree. And in fact, it's really called a prime factor tree because we have to get it all the way down until we get all prime numbers down here. Those are all prime numbers. 2 and 5 are both prime. So once we have it in all prime numbers, we want to look for pairs, and the pairs go on the outside. So that's 2 on the outside. This one doesn't have a partner, so I have to leave that underneath. That's 5 on the outside. And so I multiply 2 times 5, which is 10 on the outside. And remember, we still had that guy left over, doesn't have a partner, so that has to stay underneath. Now we also could do it the other way where we're looking for perfect squares. And so, if you just realize, hey, 100 is a perfect square, and I could write that as root 100 times root 2, and the square root of 100 is 10, well, then that's just 10 root 2. Same answer, less work. And it doesn't matter to me which way you do it, guys. Obviously, the one on the right is quicker if you know your perfect squares. All right, well, how does this tie into complex numbers? Well, if we wanted to simplify another radical, let's say we had the square root of negative 108. Well, now we have a negative. And way back when we had the square root of a negative, you guys were told, well, you can't do that. Well, you can. There just are no real solutions. There are imaginary solutions. And so for an imaginary solution, we have this symbol I, which is the square roots of -1. And what that little bit of information does is allows us to simplify this radical. So when you're simplifying a root that has a negative in it, first thing you do is poke out the i's. So the first thing I'm going to do is write this as the square root of positive 108 times I. Because I'm really doing times the square root of -1. I'm like splitting that up. And remember, the square root of -1 is I. So I'm going to write that as square root of 108 times I. And so now I just do this like the problems we were doing above, but I have an I on the end, meaning it's an imaginary answer, but I still can write it in terms of I. So I'll do a factor tree here. So I could write that as square root of 2 times the square root of 54. And then 54, I could break into 2 and 27, right? And 2 doesn't go into 27, but 3 does. I could do 3 times 9. And 9 is 3 times 3. So I've broken that down into all prime numbers. So now I want to take the pairs on the outside. I'm kind of dragging my feet to give you guys a second to catch up writing here. But I'm going to put that 2 goes on the outside. That pair of 3s goes on the outside. That one doesn't have anything to match up with, so that has to stay home. So I get 2 times 3 gives us 6 on the outside. Square root of 3 left over. And don't forget, we still have I on the end. So our answer is 6 root 3 I. All right, any questions on simplifying the radical so far? Okay, and you guys can write them in the chat also if you want to, no problem. But I'm going to roll with that and just continue to go. And when I go to the next part, well, we're going to do some complex operations. When I say operations, that scary word just means adding and subtracting or multiplying and dividing. So, for example, if we wanted to do -10 plus 8i minus 4 minus 3i, okay? We want to simplify that. -10 plus 8i minus 4 minus 3i, the quantity 4 minus 3i, or 4 minus 3i in parentheses. All we want to do is match up like terms. We're just adding like terms. So like this and this are not like terms, but this 8i and this are like terms, and this are like terms. So I'm going to distribute the negative before I do anything. So I have -10 plus 8i minus 4 plus 3i, and then combine my like terms. So I have -10 minus 4 is -14, and 8i plus 3i is plus 11i. And that's our answer. So students ask me all the time, like, okay, so do I just treat this as a variable? Yes and no. It follows the same rules as you would if it was like, you know, -10 plus 8x, but it's not a variable. I does not vary, it's the square root of negative 1. But it does follow the same algebraic rules. All right. One other piece I should have added up here. In fact, I'm going to grab this thing and well, I'll leave it there. I need to add a bit of information to that where I had I equals the square root of negative 1. Because if I square both sides, I squared equals negative 1. That fact that I squared equals negative 1 is going to help us when we are multiplying these. So I'll do one of those examples next. Let's say we have about 8 plus 4i times 11 minus 3i. Now, first things first, there's no symbol in between here like the last problem. It looks very similar, but it's way different. This is multiplication. If it's multiplication, that makes it a FOIL problem. So we're going to FOIL this one. So when I multiply the first two, 8 times 11 is 88. 8 times negative 3i is minus 24i. 4i times 11 is plus 44i. And then 4i times negative 3i is negative 12i squared. Now remember that idea that I squared is negative 1? So what that means is that this becomes negative 12 times negative 1, or positive 12. So I'll write out the next step. I'm going to have 88. I'll combine these two. Negative 24 plus 44 would be plus 20i. But now this guy is going to become plus 12, which now makes that a like term with the 88. So 88 plus 12 is 100. So our final answer is 100 plus 20i. Okay, any questions yet? Because I still have one more type of problem to do. All right, I'm going to keep rolling then, guys. Well, we did some addition and subtraction. We did some multiplication. We probably should do some division here. So let's say we have 7 minus 10i over, so divided by, negative 6 minus 6i. All right. Well, the problem is we have an I in the denominator. Remember, I is the square root of negative 1. We don't want a square root in the denominator, so we have to rationalize this. Here's how we do that. We multiply by what's called the complex conjugate. It's a fancy way of saying change that sign. If it's minus, make it a plus. If it's a plus, make it a minus. Just the middle sign, not the first one. Just change the middle sign. So I'm going to multiply top and bottom by negative 6 plus 6i. And so now this is a double FOIL problem. We got to FOIL the top and FOIL the bottom. It's going to be a little bit of work, but we can FOIL. It's just multiplying, adding. So 7 times -6 is going to be -42. 7 times 6i will be plus 42i. -10i times -6 will be plus 60i. And -10i times 6i is going to be -60i squared. Now don't forget that I squared, I'm going to have to change to a -1 in a minute. But let's FOIL the bottom before we do that. So when we FOIL the bottom, -6 times -6 is positive 36. -6 times 6i will be minus 36i. And -6i times -6 will be plus 36i. Those two are going to cancel each other out, which is good. That's how I'm getting rid of the I in the denominator. And then -6i times 6i will be minus 36i squared. All right, so our I squareds are -1. So I'm going to cheat a little bit here because this becomes -60 times -1, which is positive 60. So instead of rewriting it all, I'm just going to make that plus 60. And the bottom, that's -36 times -1. That's going to be plus 36. So I just don't have to rewrite it all. Trying to save you guys some time. That's what I'm here for. So I have -42 plus 60. So that's going to be 18. And then 42i plus 60i would be plus 102i. So that's our numerator. On the bottom, 36 plus 36 is 72. And remember, the two i's cancel out, so I just get 72 in the denominator. And so I'm almost done, but I've come really far because I'm got rid of the I in the denominator. But I do notice that all of those numbers are even, so I'm going to try and reduce and simplify that. So perhaps a number larger than 2 goes into them, but let's start with 2. I can definitely tell that they're all even. So if I am reducing, that's going to become 9. That's going to become 51. I'm dividing them all by 2. And that's going to become 36. So I have 9 plus 51i over 36. But I think maybe something goes into all of these. I know 3 goes into 9, 3 goes into 36. Does 3 go into 51? Well, I know 3 goes into 60, and that's 9 less than it. So yeah, it does go into 51. So if I divide all those by 3, that's going to be 3. 3 times 17 is 51. And 3 times 12 is 36. And so now I think I have my final answer is 3 plus 17i over 12. And I'm confident about that because 17 is a prime and doesn't go into all those. So a little bit more work for that division, but not anything that's kind of outside of the realm of what we've been doing. So we have a bunch of different types of problems that we did. Okay, just to recap here, we started off by just doing some simplifying of radicals, but then we did it where we had a negative inside. And the only difference was the first thing we did was poke out the I, put that on the outside, and then simplify like we did before. And then knowing that I is equal to the square root of -1 and I squared equals -1, we then were able to do some operations. So we had, two examples where we were subtracting and then multiplying. And then we finally did this long one at the end here where we were dividing. And so to do that, we had to multiply by the top and bottom by the complex conjugate.